In this video, we'll be transforming the binary search code that we wrote in Python into C#. We'll also talk about why this has a time complexity of order of log n. So let's go ahead and get started. Now, this is the code that we have in Python, and we'd like to convert all of this into C#. So I'm going to copy the whole code and paste it in as a multi-line comment that we will then use to translate into C#. So the first thing that we want to do is cut this line and paste it in. Now this is a comment in Python that we want to transform into C#. Now what we want to do is we want to write a function that searches for the target value in a sorted list. Now, so what we need to pass to it is a value that we are looking for, such as this variable here or argument. And we also need to pass to it a sorted list. Now, it's really important that this list, or if you're passing an array or a vector, that regardless of what you're passing in, it needs to be sorted because the binary search works based on order. So if you give it an unsorted list, it won't work. Okay, now what I'm going to do is I'm going to put this comment down here and keep working with that. So we've got a function there, but we don't have define as in the keyword define. So what we do is we will translate that to a static function. And this function pretty much returns an integer because if we look at the return types, we've got mid is an integer, but we also want to put into consideration the return at the end. If the target is not found, it actually returns none. And one thing to keep in mind is there isn't a non-keyword in C# like we have in Python. Instead, we've got the keyword null. So it should actually be null. This is to represent the absence of a value in C#. But in C#, when you say static int, you can only return an int. It doesn't represent a nullable type. So to make it nullable, or to make it support nullable return types, we add something called the nullable modifier. So what it's going to do is it's going to allow the value type of int to be returned. In addition, it'll allow it to hold a null as a possible value in addition to the possible range as an integer. So in this case, we've used that nullable modifier as a shorthand to make this integer type nullable. Okay, I'll talk more about this in a separate video, but let's keep on going. The other thing that I want to change is use the convention of Pascal case instead of the snake case. That's because that's the convention. Now, as we can see, the main is capitalized. So I would like to use the Pascal case here. So binary search. We do need to specify the data types in C#. So the data type of the array is basically, I'm just using an array. We don't have the colon. Instead, we have the opening and the closing curly braces. Okay. So let's keep on going. That's a comment. The first element index, we do need to declare them and specify the data type. So the first element, 0 is going to refer to the first element in the list. And let's keep on going. Now the last element, so I'll cut these 2 lines. I kind of lost my multi-line starting comment, but that should be okay. Again, same thing. And I did forget one thing. I don't know if you've noticed, I forgot the semicolon. That's not something we need in Python, but we definitely need it in C#. Okay. Now the other thing is we don't have a length function. Instead, we will use the length property of the array. So array dot length, that will give us the length of the array. -1, that remains because you always get an extra value, right? Because we start from 0. So if this array is actually 5 elements, but we want -1, 4 because we start 0, 1, 2, 3, 4. So this is going to refer to the last element in the array. All right. Now what we do is we will keep converting the code into what we call C#. So that's a comment. Continue searching while the search range is valid. So we've got a while. The while is pretty much similar to what we have in Python. We will use the parentheses there and get rid of that colon and have an opening and closing curly brace. Next, what we want to do is calculate the middle index. So keep that as a comment. And this is the first time we talk about mid, so we need to declare it. Left plus right. Now we don't need to use this convention as we did. This is an integer division that we have in Python. This will be implicitly done. If both left and right are integers, it's automatically going to be an integer division. But let's not forget the semicolon there. Next, what we have is the target. If the target is at mid, we will return the mid because that's how it works. That's how the binary search works. So let's see what we would change now. The if is in parentheses, and we get rid of the colon. Pretty much that part remains the same. I would like to keep it in curly braces, even if it's just one line. I think that's a good convention to do. All right. Now, where are we? So what's happening? Target is smaller, we search the left half, but if target is larger, we search the right half. So let's do the magic and change things to C# and say goodbye to Python in this video. Not forever. Okay. So if it is smaller, we don't have an elif, so it's actually else if and such. Parenthesize everything, get rid of the colon, put things in opening and closing brace to indicate that's our block. So in Python, if you noticed, the way Python recognizes a block is through indentation. So as soon as you do wrong indentation, it'll complain. But it's not a Python tutorial, so let's go back. But I thought I'd mention it. Now the last part would be if the target is larger, then we search the right half. So that else looks pretty good, but we do want to get rid of the colon because it doesn't make sense in this context. And because we've already declared left and right, there's no such changes that we need to do here other than adding that semicolon to indicate it's the end of the statement. So that's the end of our while loop. And if our search has finished, so that's the end of the while loop. If the while has ended and it didn't find anything, that's when we want to return none, but we don't really have none in, like we said, in C#, return null instead. So return null, not nil, null. Semicolon things and close it off. Now let's look at our main. Let's cut all of this, put it into main. Okay, so in main, what we're going to do is we're going to declare our array, square brackets to indicate that this is an array, and it will be equal to all these nice looking numbers. That's our array. Next example, let's keep that as is. That example has to be turned into a comment. Now, one thing to keep in mind is that we don't have print, we have console dot write line, and we want to use the same convention, Pascal case, and we will pass the target that we're looking for and the array, and all of these should be comments as such. Oh. Okay, I think, and I'm going to need the semicolon. I keep forgetting that one. So what I'm going to do is I am just gonna sort of do this. It's just easier if I had done things correctly. And then just search for different items. and 16. Let's search and see what mistakes we got. If Oh, we got lucky. We got lucky. This is pretty much working exactly like we thought it would. We do notice one thing though, is that the null is not showing. The null here is not showing. And that's because in C#, if you're trying to print null directly with console.writeLine, like as such, then it's not, it will just print a blank line like we have it, a blank line like this. So I think I'll make a different video on this to show how to print null, just to keep the time frame of this video reasonable. Now, one thing I wanted to do is the comments here. This will explain how we've got the time complexity, but I've already sort of done that like what I've done is I've copied this and transferred everything into a C# comment. So I'm just going to paste it here. So the time complexity of the binary search is in the order of log n. In the best case, it's in the order of 1. And I'll show you why and how that works. So in the case we're searching for the number 11, the mid is going to be at 13. And so what it's going to do is it's going to search this part of the array. And if we're looking, say, for 14, then it's larger than mid, then it's going to search the right part of the array. So that's pretty much our algorithm here. So if the target is smaller, search left side, but if it's larger, search the right side. So if 14 is larger than the target, which is 13, and we're searching this part, it is less, we're searching this part. So the binary search is always splitting things in half. But when do we get the constant time? The best case is when we get the best case is what if the target element is in the middle, like this one in here, is right in the middle. And during the first comparison, the binary search completes in just one comparison. So the best case is actually this part when we return mid on the first go. So it only runs one time pretty much. But in the worst case, it will require log base 2 in comparisons to find the target or determine that it's not in the array. Now, this occurs when the search has to split the array down to one element. So I've got something, because the algorithm halves the search range each step. Each comparison removes half of the remaining elements, so the number of comparisons needed to find or not find the target grows logarithmically as the list size increases. So let me just show you again what we need is when we're searching, for example, when we're searching for the value 14, we needed 2 comparisons, because the second, so this is probably a better way to show. When we search for 13, the first time it finds it because it's equal to mid. So that's the best case. Now, for searching for values of 11 and 14, that's 2 comparisons. In an array of 5 elements, the maximum number of comparisons it needs to do is 3 comparisons. That's including if we were searching for a value that doesn't exist, like 16. So it's also 3 comparisons. Now, let's have a look at this part here. That's an interesting part. Is if we have an array size of 16, we need 4 comparisons. So that's a log base 2 of 16 gives us 4 comparisons. And if we double the size of the array, then it's 5 comparisons. And if we double, it's 6. And double 64, so 64 times 2 is 128. So then we need seven comparisons. And then for an array size of 256 elements, we need 8 comparisons. So the pattern that we see is that each time the number of items doubles in the array, the search algorithm requires only one additional iteration. And that's why we have a really good complexity of log n, even in the worst case. I hope this video really helps you.